Morning, everybody. And so today, for the third lecture, I will focus on another aspect of quantum measurement theory. As I told you yesterday, I will focus on the problem of the Schrödinger cat, the decurrence and Schrödinger cat, which is related indeed to the problem of considering the role of the environment in the way a quantum system becomes classical during a measurement. So just a brief reminder of the two first lectures. The first lecture was devoted to describing the strong coupling regime in cavity QED, and it was illustrated by the cavity QED experiment we realized in Paris with circular Rydberg atoms interacting with microwave photons stored in a cavity. Then, in the second lecture, I told you how to use this system in the strong coupling regime, but not with a resonant interaction, with a non-resonant interaction, in order to perform quantum non-demolition measurement of the number of photons stored in the cavity. And basically, the principle of the experiment consisted in building an atomic clock with the circular Rydberg atom. The principle of the atomic clock was the Ramsey setup of separatory oscillatory fields, or in short, the Ramsey interferometer, in which a superposition of atoms is prepared before crossing the cavity, then flies across the cavity, and then a phase shift of the coherence of the superposition of the clock indeed appears during interaction with the cavity, which is proportional to the photon number. And then by probing this phase shift using the second pi/2 pulse in the second Ramsey region, we close the clock. And then we have seen that if you consider not a single atom, but a collection of about 100 atoms, this collection of atoms is already a macroscopic enough clock so that it plays a role of a needle of the meter, which points on the photon number, depending on the phase of the clock, depending on the position of the needle of the screen. So we have seen a first example of a model of measurement apparatus, which shows you how to realize in practice a measurement apparatus, which indeed works as a state in the postulates of quantum theory. And we have seen that this leads to the observation of quantum jumps, these famous quantum jumps, which were predicted by the quantum theory since the early days, but to which even Schrödinger was not convinced that they would be never observed, and he qualified this as unphysical. So I hope you are now convinced that these quantum jumps are physical. And now we have really a model of ideal measurement apparatus working as the postulates with this famous projection postulate, with the subtlety that you see that instantaneous projection is never instantaneous in a real world. Projection is not kind of magic things. It's at the basis, first, interaction between the system and the meter, the system and the probe that we want to use to measure it. And then after this interaction, which builds entanglements and correlation between the two systems, we extract the probe from the system, which does not interact anymore with the cavity field. And that's by performing indirect measurement on the probe system that we project the state of the field inside the cavity. And indeed, at the result of readout of the atomic state by measuring the average collective spin of the atom, we were able to reconstruct the various positions of the atomic needle pointing in different directions for different photon number in cavity. And when I've shown you that when the first measurement gives you the result of 5 photons, you observe as a function of time evolution of the needle, which jumps abruptly, not instantaneously, but abruptly as compared to the time scale of evolution of the field, which is the cavity damping time. At that scale, cavity damping time is around there. So the first jump occurs more or less after one cavity damping time. So that was the point of my second lecture, how to achieve a projective measurement conform to the postulates, and there are not so many systems where you can do that. So it's amazing to see that the founding father of quantum mechanics invented this postulate without the possibility to have really tools to perform this and to clearly demonstrate the projection of the quantum state. So now, for the third lecture, I will basically look at the same experiment, so an atomic clock observing the field in the cavity, but I will reverse the point of view between the field and the atom. Up to now, the atoms were used to measure the field. Now, I will consider the field as a way to measure the active atomic state, and then the kind of matter, which is a small coherent field stored in the cavity, will have a very nice quantum behavior in terms of Schrödinger cat, allowing for observing the role of decoherence in the fact that you have a pure state after interaction, which is somehow converted in a statistical mixture during the full quantum measurement. And so the goal today is to look into this problem of the transition from a coherent superposition state of the system to be measured, which will be the atom and the cavity state, and a statistical mixture which corresponds to the right mathematical object to describe the state after measurement occurs. So that's the title of this second lecture. And then I will just put the specific case of our experiments in a kind of more general context, because I think that this is very general and applies to any kind of system. Where basically, when you want to perform a measurement, you have a system which is isolated that you want to measure, and then you send a probe to get information about this system. And in general, if the probe carries information of the system, it means that the evolution, I suppose here that this evolution is Hamiltonian, leads to the production of an entangled state where there are quantum correlations between the state of the probe and the state of the system you want to measure. And then I consider the scheme of indirect measurement where the probe goes out of the system, which means that it does not interact anymore with the system, and I try to get information on the system by looking at the probe. And one element which was not present yesterday in my discussion of this problem is the role of dissipation when the probe starts to herself interact with the measurement apparatus, which is at some point such a huge system that it cannot be considered as insulated. And I think quantum physics is the physics of open system at some point. You cannot avoid that. And then after interaction with this kind of dissipative environment, if you choose properly what you measure on the atom, you perform a measurement which tells you something about the state of the system. So that's the general framework. And so today we will focus on this part, the role of dissipation and the way you have to design a measurement apparatus so that it is a good measurement apparatus. And you will see that a measurement apparatus measure observable which are related to the robust observable with respect to dissipation. That's one of the carry home message I would like to give. So now I will also make just a general introduction about the Schrödinger cat problem and show you this famous picture introduced by Wojciech Zurek in the beginning of the 90s, where he pointed out this problem of transition between quantum and classical world and the problem of coexistence of these two logics. Also, everything, including the classical world, is made of quantum particles. So how does it go that these quantum objects, when put together for doing a big system, have a present kind of a classical behavior? And so the decoherence concept was formalized by Zurek at that time. Also, it was also already present in the mind of the founding fathers of quantum theory, as I said in my introduction yesterday when I was considering the trajectory of a charged particle in a bubble chamber. So the role of the environment was already considered by the founding fathers of quantum theory. So the Schrödinger cat problem, brief reminder, you more or less all probably already heard about that, but I just rephrase it briefly in a kind of original form. You take a quantum system, a radioactive atom, that will decay randomly at some time, and then together with the atom, you put a Geiger counter, which detects eventual disintegration of the particle, and then you imagine a chain of events connecting the result of the measurement displayed by the needle of this Geiger counter to a kind of diabolic system that I do not recommend to build, which is a hammer breaking some bottle of poison, which eventually will kill the cat when the nucleus decays. And then the story is that you assume that you put all this in a box, which is completely isolated from the rest of the world, and you ask the question, what is the state of the cat and of the full system inside the box before I look at it? And indeed, if I wait for half the lifetime of the radioactive particle, you know that there is a probability 1/2 that the cat is unfortunately dead due to decay of the particle, and 1/2 that the cat is still in a good mood because nothing happened. And then the question set around this problem is, when does it happen that nature decided whether the cat is dead or alive? And if the box is closed, completely isolated, Hamiltonian evolution occurs as the only evolution process, which means that you expect that you have a quantum superposition of the two possibilities. And then a paradoxic way of formulating the problem is to ask the question, does the cat dies or stays alive only when you open the box and look at it? And that's the kind of question we'll try to answer today. Of course, if I anticipate, because I think you already heard about that, the message today will be that nature looks at the state of the cat well before you look at it, because the box cannot be completely ideally isolated as expected here when the system becomes too large. So this has to do, indeed, formally, with the transition between an entangled superposition state involving macroscopic object, let's say a cat, and a microscopic system, let's say one atom. So just a remark here, when considering this state, I think that this example with radioactive decay is very famous, but it's probably the worst example to illustrate that, because at the beginning of the process, you have irreversible exponential decay, which is not the best and simplest system for considering coherent evolution. And you already have to include a very huge environment just at the first step of disintegration. But this is anecdotic, but I think the Schrödinger cat prepared not by a decay process, but a coherent process is probably easier to consider. And that's the kind of cat that we will consider. So one question people ask is, does the state really exist before you open the box? And I will consider this question not from a philosophical point of view, but I am an experimentalist, so I will have a much more practical formulation of this question. Can one perform an experiment demonstrating the superposition between these two states? Can you arrange a setup so that you can interfere the two probability amplitudes related to these two states, which would be an experimental signature of the existence of the cat state? So that is, of course, a question of the quantum theory of measurement. The cat presence is just anecdotic to make the thing eventually more strange for the mind. But of course, the problem is already there at the level of the needle of the measurement apparatus. The Geiger counter already does the work. So the kind of state I will consider is not a real huge macroscopic cut, but the needle of the measurement apparatus, which will be of a variable size, which can be varied from microscopic to more macroscopic to observe the transition between classical and quantum behavior in our system. So here is a resume of the properties of measurement I will consider today. And indeed, the question is to know whether a real measurement provides a definite result and a single one, or just superposition of results. And then I think it's interesting to state the answer of Schrödinger to this problem, because Schrödinger was the one who was introducing this Schrödinger cat problem, probably not considering that this will become so famous. Because indeed, Schrödinger eliminated the problem in a very radical way, saying that obviously this should not exist, and it's ridiculous to consider that. So that was one of the ridiculous predictions of quantum theory, that he considered that will never be observed in any way. So another formulation of the problem is that when you perform quantum mechanics, so you calculate the evolution of the system, unitary evolution can prepare states which looks like unphysical. So we can more precisely formulate what is unphysical, but our intuition is that the physical result is either that or that, and not a superposition of this. So it looks that the Hilbert space is too large to describe actual quantum system. And then the idea is that even if the system is too large, what I want to show today, even if the Hilbert space is very large, there is another way to define the classical results independently of what I think. So Schrödinger suggested that ridiculous states should be eliminated. Of course, in physics, we don't like a theory which relies on what you think about the system. You need a more objective definition of what is an allowed state or not. And indeed, that's the decoherence approach which will provide this mechanism, and which will make a physical difference between allowed states and not allowed states. So that's when including dissipation, I think, to the problem that we can shed light on that question. So my point today will not to write a lot of equations and to formalize all this in a general way. Indeed, there is no general theory of decoherence. It's just standard quantum mechanics. And then decoherence is a model that you can build for each apparatus by looking carefully at the way it interacts with the environment. You can say, okay, what is measured is that observable rather than another one. So what are the objects? Of course, it's again the same partner, the cavity field and the single two-level atom. But now I told you I will reverse the role of the cavity field and the atom. Up to now, the atom was measuring the cavity. Now, the matter will be the cavity field state, and it will be used to observe, to measure the atomic state. And I will need to be a bit more specific about the kind of state we use in the cavity in order to perform this measurement of the atomic state. So I will again consider the coherent superposition state of photon number, the coherent classical field state, or the Glauber state I already introduced in my previous lecture as this superposition of number state, which have a Poisson law distribution. Here I have represented the Poisson law with average photon number 2 and fluctuations which scales as the square root of the number of photons. And what will be of interest to me is to use the fact that when you go to large photon number, this object becomes more and more classical. And I will try to show along the lecture what is the meaning of that. So a first meaning is a very simple one that you can find easily in the textbooks of quantum mechanics. When you introduce these coherent states, either for describing a classical field state or for describing the classical state of any mechanical harmonic oscillator, it's nice to say that the average value of the amplitude of the field, so these two axes corresponds to the two quadrature of the field stored in the cavity. This is represented as a vector. That's the C number representation of classical fields. Or if you prefer the picture of Fresnel plane, the amplitude of the field is a vector in a Fresnel plane. This vector here is dimensionless because alpha was built as dimensionless parameter, and you have to put a factor with the dimension of the electric field to have the electric field amplitude. But here we'll only consider dimensionless amplitudes. And so that's what you figure out in classical electromagnetism. If you have a classical field with some complex amplitude, it's just one vector, one point in the complex plane. Then, if you consider it more quantum mechanically, you have to consider quantum fluctuations, which indeed, in the case of the coherent state, corresponds to a kind of circle with it, where you can figure out that the end of the arrow points. And indeed, the diameter of the circle is 1 in this dimensionless space. And indeed, this circle is just the same as the vacuum fluctuation circle. If you represent vacuum fluctuation by a circle with a radius corresponding to the variance of the field amplitude, this circle is a unity diameter, and it's just translated at the top of the arrow representing the amplitude of the field. And you see already a first way to make a transition between quantum and classical is alpha is very small. The quantum fluctuation will dominate, and you cannot avoid to consider the field as a quantum object. But if, on the other hand, you take large enough alpha, corresponding to large enough photon number, large enough means that the photon number should be much larger than 1, then the phase fluctuation, for example, and the amplitude fluctuations becomes in the relative value smaller and smaller. And if you consider the angle corresponding to the diameter of this circle at the top of the arrow, it scales like 1 over modulus alpha, 1 over square root of the number of photons inside the cavity. So you see that when the amplitude of the field gets larger and larger, the relative role of quantum fluctuation with respect to the average value of the field becomes smaller and smaller, and you expect that the field becomes more and more classical. So that's the first argument. Another one, which is eventually even stronger, will show up later, which is the decoherence argument. But it will be rather for the conclusion. So here is the object, and basically I will use a field with a variable photon number as a needle, and I will try to make the experimental arrangement so that depending whether the atom crosses the cavity in upper or lower level, E or G, there is a phase shift of this needle which is larger than fluctuation, so that the position of the needle defines unambiguously the state of the atom. So for this, I will need a little bit of more formalism for describing the coherent state. So I think it's good to have this in mind because it's simple mathematics. And indeed, as soon as you consider a coherent state of a field of harmonic oscillator, it's very instructive to consider this operator named the displacement operator. So this is unitary. You can easily check that. And so it expresses the exponential of A and A dagger operators. And it's defined for any complex number alpha. And the interest of this operator is that it generates coherent fields when you apply it to vacuum. So d alpha over vacuum creates a state which is nothing else that coherent state with amplitude alpha I have just written. So this can be easily demonstrated using this equivalent expression of alpha when I use the commutator between these two operators to break the exponential in two. And if you make this operate on vacuum, the Heidegger term does nothing, so vacuum remains vacuum. And this creates exactly the amplitudes you have there. So you can check this as an exercise. So this operator is a very compact way to write the expression of current state. And then there are a very nice formula when you make this operator act not only on the state, but on the operators. And it's interesting because it's a unitary operator. So it can describe some evolution. And so if you apply the displacement operator not on the states, but on A, it produces a translation of the operator by a complex number. If you combine two displacement operators, you generate the sum of the two C number alpha and beta with some phase in factor, which is a global phase for the state. So the displacement operator is formally the way you can, by applying to vacuum, produce a translation in phase space, which not only translates the vacuum to alpha, but any state beta to alpha plus beta. And so that's a very interesting picture to have in mind that when you have this operator at hand, you can perform arbitrary translation of the state in the phase space. And indeed, the even more interesting property of this operator that you can find demonstrated in textbook is that it corresponds to the unitary evolution operator describing the interaction between a classical source and a quantum field. So what do I mean by a classical source? Let's assume that there is an antenna somehow coupled to the cavity with a current that I consider as a classical current. And then I write the Hamiltonian of interaction between this current and the field operator. So it's a semi-classical approach where one object is a sinusoidal real oscillating function, the amplitude of the current in the antenna, and the other object is the electric or magnetic field in the cavity. And if you write out the evolution operator corresponding to this process, it generates a coherent field in the cavity. So that's the formal arguments that we use to say that we have, when we have a classical source coupled to a cavity, it radiates a classical field. So without knowing it, everybody doing broadcasting is radiating a quasi-classical state. Usually quantum fluctuations are so small that we do not care. But today we will deal with quasi-classical field containing 1 to 10 to 20 photons, which are really mesoscopic objects where quantum fluctuation cannot be neglected. So then let's go into the heart of the experiment. So you recognize the same setup as I used yesterday. I consider exactly the same setup, where I have again the two interactions with a classical microwave source forming the Ramsey interferometer. The atom is prepared in this first interaction zone, the superposition of E and G, crosses the cavity, and under the effect of non-resonant interaction, indeed, one expects that depending whether the atom is in E or G, the phase shift, the field will experience a phase shift which will depend on whether the atom is E or G. So what is the origin of this phase shift of the field? So if you write it, the state with the shift of the energy level that you find with the dressed atom, you find easily this result, but I will give a simpler physical picture for this. Indeed, when the atom goes into the cavity, it has some polarizability, and somehow it changes the index of refraction of the media inside the cavity. Instead of vacuum, it's one atom. And if you put a piece of material in a cavity, you change the resonant frequency. And here the point is that you change the resonant frequency, but over a time scale which is much shorter than the lifetime of the field in the cavity. And indeed what happens is when the atom enters the cavity, it is as if the distance between the mirror was changing slowly with a Gaussian profile, because the mode is Gaussian. And then the field energy cannot be changed, because this is such a slow change that every photon number keeps its population adiabatically, but you accumulate phase shift, and the result of the accumulated phase shift of individual photon number state is a global phase shift of the current state. So what is amazing is that a single atom is a good enough medium so that you have a sizable phase shift in the system. So that's related to the extraordinary large polarizability of circular Rydberg atom, even if the interaction is non-resonant. The dipole matrix element between Rydberg level is so large that you can produce a macroscopic phase shift of the field. So what is the magnitude of this phase shift? Here you recognize that the phase difference between the two components of the field will show up. So first, the point is that depending whether the atom in E and G, the light shifts are positive or negative, which means that one level looks like having index of refraction larger than 1, the other smaller than 1, and the accumulated phase shifts are just opposite to each other. And then the phase difference between the two components is nothing else than the phase shift phi 0 I already introduced yesterday as the phase shift induced by a single photon to the atomic coherence. So it's the same phase shift, but now it describes a kind of macroscopic effect on a quasi-classical field. And so now, if you consider that the atom is not either in E or G when crossing the cavity, but in a superposition state E plus G prepared by this pi/2 pulse, you expect the field, the atom field system, to be prepared by a unitary evolution is an entangled state written here, where you have a superposition of atom with a field with a phase plus phi 0 over 2, and the atom in state G with a phase shift minus phi 0 over 2. And indeed, the coherent superposition there, the phase of the coherent superposition is related to the phase of this pi/2 pulse, so it's really controllable phase. And for the given experiment, for example, if I choose the phase properly so that the rotation occurs along the y-axis of the Bloch sphere and prepares the superposition E plus G, we have the sign plus. So we have full control about this. So then the end of the story is just as before for detecting the number of photons in the cavity. I let the atom finish to fly until the detector, and before going to the detector, the atom will be submitted to a second pi/2 pulse. And so this second pi/2 pulse will split the E part of this state in E plus G, the G part of that in E plus G, and E minus G. And in the end, the detection of the atom, okay, this I should have dropped the E and G terms here, so that once you detect the atom, you know whether the atom is in E and G, but as you don't know whether this E and G comes from this part of that part of the wave function because of this kind of pulse which somehow erases this information, you project the field in the superposition of alpha E phi naught over 2 plus alpha minus E phi naught over 2 without entanglement. So here the goal was to describe the state after projecting the atom. And then the sign plus or minus here after this detection depends whether you detect the atom either in E or G. So you see that you can generate two kinds of Schrödinger cat states in the cavity by this measurement, depending of that measurement result. And this is not anymore an entangled cat, but it's already what is usually considered as a Schrödinger cat state of the cavity field. And now the challenge is to try to experimentally fully characterize the cat state prepared in this experiment. And I will present the way we did this by performing a quantum tomography of the density operator describing the field prepared by this experiment. So let me mention before doing this characterization of the cat by quantum tomography that we already performed a first demonstration of the preparation of the cat in the cavity in the old generation of the setup, with the cavity was not so good. So at that time, it was not possible to perform full quantum tomography of the state of the cavity field. And indeed, we made a kind of partial characterization of the cat state for kind of small kitten involving only up to 3 photons in the cavity. And the idea is to build a quantum interference by doing a 2-atom experiment. So the first atom split the state of the cavity into 2 phase components, and then the second atom splits again each of these components in 2. And you see that when you do that, you have one field component with the original phase, which results from a quantum interference between 2 passes. And this quantum interference is sensitive to the cat coherence, and that's what we measured in this experiment, where we had the first insight into decoherence. But I don't want to give you more details about this, because then we perform with a better cavity a full tomography of the Schrödinger cat state, and I will comment the way we obtain this and comment the properties of the cat state we can demonstrate by doing this tomography. So what is the method of state reconstruction or state tomography that we used? Okay, so that is a general scheme. When you want to perform tomography of a quantum system, you have some state which is supposed to be unknown and represented by a density operator rho. Then you couple this system with a measurement apparatus. You measure some set of observable that I will name here Gi, and then you get a set of measurement results for each measurement. You get measurement value. Of course, when you perform this measurement, you have to prepare every time rho in the same state to measure another observable. And so you don't measure a repeated observable, you measure independently the different observable. Each of them gives you some information about the system. And indeed, once you get a measurement result for observable number I, you get a constraint on the density operator of the system. If you measure a large enough number of times the same observable, you get the statistical noise is reduced, and you can consider that the average value of the results, Gy, gives a constraint for the density operator. So this is usually a linear constraint, and if you measure a large enough number of operators, forming what we call a complete set of observable for characterizing the state, you expect to fully determine the density operator using this set of linear equations. Indeed, this is the simple principle, which works only if the measurements are noiseless. In the presence of noise, of course, you may, the inversion of this set of linear equations may lead to a density operator with negative eigenvalues that we don't like very much. So we have to play some mathematical trick to avoid this effect, which is induced by noise, because all measurements are always taken for finite time with some statistical errors. And so the reconstruction method cannot be just linear inversion, but have to take into account the noise and lead to physically acceptable system. Let's say density operator, which have to be positive. So there are various ways to do this. And indeed, before going to this mathematical way, let me comment the first point is that we need to have a complete set of observable. So let us come back to a system which considers the density operator of the field, which have, in general, this form. So the index here is the number of photons. So the diagonal represents the photon number distribution, and the off-diagonal terms represent coherence between the various photon number, which are already present in the quasi-classical state alpha that I have discussed before. So in the previous lecture, I have shown you that if you send large enough number of atoms through the cavity, you can deduce the photon number, and then you can reconstruct the diagonal of the density operator. So that's what I've shown in the second lecture. And now we have to design some measurement operators performed by the atom on the cavity in order also to get information about the off-diagonal matrix element of the density operator. So how to measure these off-diagonal elements? Well, the method is kind of straightforward. Instead of measuring the photon number for the original field state, which is the red thing here, I will measure the same observable, but after applying a shift of the density operator in the phase space. And the shift is nothing else than applying a displacement operator. Displacement operator means that once I have prepared this, which will be a Schrödinger cat state, I switch on a microwave source outside the cavity with a little bit of coupling, and the field radiated by this classical source will produce this translation with well-defined amplitude and phase if I adjust properly the amplitude and the phase of the source, the synthesizer, that is coupled to the cavity. So this step is very easily done. I switch on the source for a short time. It shifts the density operator in the cavity. And then I perform the same measurement as before. I perform measurement of photon number. And if you look into the effect of the displacement operator over the density matrix of the field, it's a linear operation of matrices, which mixes, it does not mixes, it makes superposition, linear superposition of all coefficients there, diagonal and off-diagonal one, which means that in the displaced state, the off-diagonal elements are injected somehow in the diagonal, and the superposition of them with some interference term, but which means that when we measure the photon number after displacement, you learn about off-diagonal photon number information, off-diagonal matrix element of the density operator. So that's the trick, and then you have to have a large enough number of displacement in order to fully determine the density operator of the field. Indeed, in practice, what we do is to measure several hundreds of displacements, which are spread not over the full phase space, because it goes to infinity, but in a bounded region corresponding to about up to 20 photons in the cavity. So we do this, and then we get a lot of information, and we have to deal with the noise of the measurement in order to reconstruct the density operator. So instead of doing linear inversion, we could try to find, to fit the operator, eventually with constraint, but there are more efficient strategy, and the two one I would like to mention is the maximum likelihood strategy and the maximum entropy strategy. So the maximum likelihood consists in finding the density operator which maximizes the probability of the list of the measurement results that you produced. So for the original state, you measured a lot of atoms, and you have a list of the measurement results. Then you make a displacement operator, and you have another list of measurement results, and you put this list together for many displacements, and you have a huge list of E, which are all the measurement results for thousands and thousands of atoms having crossed the cavity. And you can calculate the probability to get this special list of E and G events in order to find the density operator which maximizes the probability to observe what you have observed. And indeed, this is an efficient way to characterize the density operator of the field. It is used not only in the context of cavity QED, but with many different quantum systems. So a second strategy that we choose here is a maximum entropy strategy, where basically you find the density operator of the field which does not maximize the likelihood of what you observe, but which fits the measurement with the additional constraint of maximizing the entropy of the reconstructed state, which means that it's kind of a choice when you are kind of paranoiac. You can say, okay, maybe I have not measured enough information to fully characterize the field, and then I take among all the kind of density operator which fit the data, the one which is the worst in terms of entropy, so that I have no more information in the reconstructed state as compared to what I have measured. Indeed, in practice, we perform both, and they were equivalent. So we both maximum likelihood and maximum entropy, which means that we were measuring enough observable to fully determine the state. And in these two approaches, we are looking for a well-behaved density operator. It's mathematically expressed in the algorithm, which means that we never get unphysical operators with negative eigenvalues. So that's the way we reconstructed the density operator. And what we reconstruct from the measurement is the density operator of the field prepared after detection of a first atom. So then, in the experiment, we prepare the state to be measured, let's say the cat state. Then we measure some observable G for a large number of different displacements in the cavity. So we perform, depending on the state, from 400 to 600 different displacements in the complex plane to fully characterize the field. And then we use the maximum, we apply the maximum entropy algorithm. And then we'll use a representation of the density operator, which will not be direct representation of the matrix elements, which are complex, and it's 2D matrix. It's not very common, convenient to represent the state by looking at density operator. We'll rather use a very common representation in quantum optics, which is the Wigner function. So maybe some of you are not familiar with the Wigner function, so I will introduce it briefly. So the Wigner function was introduced by Wigner historically to describe the state of a massive particle characterized by operators x and p. And indeed, writing the Schrödinger equation in terms not of density operators, but in terms of Wigner function is a nice way to make a transition to statistical physics equation for describing the gas, for example, and to recover the UV equations that describes the evolution of a collection of classical particle with position x and p. So what is this distribution? So you can consider it as a kind of generalization of the probability distributions that you already know when considering a particle with position x and momentum p, which is the probability distribution of position defined as the trace of density operator times the projection of the position of eigenvector x, which can also be expressed in terms of a trace of density operator times this delta operator, where the argument is the operator x minus the number x. The same holds for p. You can get from the density operator the probability density of p. And then in classical mechanics, you can define also a joint probability density for variable x and p. And if you generalize this concept to quantum theory, you can consider this distribution, which is so-called the Wigner distribution, this defined as the trace of density operator times the product times this two-dimensional delta function, one for x, one for p. So if quantum theory was classical, I would say, this is nothing else than joint probability distribution of x and p that you use in statistical physics for describing the equation of a gas. In quantum physics, it is not, and the mathematical reason, consequence of the quantum property of this system, which is related to the fact that for a given particle, you cannot have a perfect determination at the same time of x and p. And the consequence of that is that this distribution, this joint distribution, can be negative. So you cannot interpret it as a probability distribution in general, because probability distribution should not be negative. And then it is very often considered that negativity of the Wigner function of a quantum state is a signature of its quantum character. And then this object is also very nice, not only for representing graphically the quantum states, but indeed, one can show that it can be considered as mathematically completely equivalent to the density operator of the system. And you can calculate average value of any operator using the Wigner function instead of the density operator. So I have written here another equivalent mathematical expression of the density operator that maybe some of you already know, so that they can recognize the thing. So you can go from here to here by kind of operation with Fourier transform. And here you see that the Wigner function is kind of Fourier transform of this matrix element, which is off-diagonal matrix element of rho between these two position eigensters there. And here you have this factor characteristic of a Fourier transform. So that's the object I will use for characterizing the state of the field in the cavity. And then I write here the quantum optic version of that. How you go to x and p position and momentum of a particle to the observable of a field. Let's remind you that harmonic oscillator, mechanical one, and field harmonic oscillator have a one-to-one correspondence. If you make a correspondence between x and p position operator and momentum operator of the particle with this big X and big P, which are combination of A and A dagger operator, which are called in quantum optics the quadrature operators. So you forget about a position of massive particle. You write the same equation in terms of this quadrature of the field, and you get the Wigner function of a field in the cavity that we usually express as a function of complex parameter alpha instead of x and p by introducing alpha equal x plus ip. And then I will use an alternative expression of this Wigner function to illustrate the experiment. So you have this expression, you have that, but the most interesting for us, and I think it was already introduced by Glauber, is this expression where W of alpha appears at the trace of density operator times this, which is an emission operator. So this shows that the Wigner function is an observable for the field. And what is the observable there? You recognize displacement operator, here the alpha. And here, this operator gives a phase to the state, which depends on the parity of the state. You see that for, this is the photon number operator. For even photon number, this is 0 modulo 2, and this produces no phase shift. If you consider odd photon number, this operator is -1, and it produces, it flips the state. So it's nothing else than the parity operator characterizing the parity of the field state. And what is measured here is the parity after displacement of the state, because when you have a trace, you can put this displacement before rho, and then rho sandwiched between two displacement operator is nothing else than a displaced density operator. So the Wigner function is a parity of the displaced density operator in the case of the cavity field. And that's what we measure, because I have shown you yesterday that when we have a pi phase shift per photon, the atom measures the parity of the field. So this parity measurement is used here to get information about the Wigner function. So here, example of Wigner functions, which are not reconstructed operators, but that you can find in textbooks and you can plot easily. So the first Wigner function represented here is that of a coherent state with amplitude beta. So indeed it is a Gaussian distribution, which is always positive, and which already gives you the idea that the quasi-classical state I have introduced, the beta here, are well behaved as classical objects because they don't have negativity in the Wigner function. And in quantum optics, you probably already heard that if you want to use quantum states from quantum optics to performing some interesting quantum information operation for example, for quantum computing, current states are not good candidates, they are not quantum enough, and you need to transform them so that you get some negativity of the Wigner function. So it's not the topic of this lecture, But here you have the Wigner function. The origin is here, so the distance to the origin is the modulus of beta. I think it's modulus square of beta. Here I choose a state with 2 photons on average. And basically, when the probability, the Wigner function is probability, you can have a kind of appropriate representation of the field as a statistical classical arrow fluctuating within this Gaussian. And you can have this picture in mind for describing your system. Then I have presented another example, which is more quantum, which is a Wigner function of a number state. Well, there are 2 important features. Now the Wigner function is not shifted, it is centered around 0. And you see that the average amplitude of a field containing 1 photon is 0, and it's purely fluctuating thing. But these fluctuations are more quantum than the vacuum one. This one of the current state are the same for vacuum, because vacuum is a current state with beta equals 0. So here, that's quantum fluctuation, but Wigner function becomes negative. So I would say that's more quantum fluctuations. And negativity of this Wigner function of the 1 photon state makes these states more interesting for information processes and compared to coherent state. So let's go to the state of the experiment. So I assume that we have performed all the measurement of the parity after displacement of the cavity field. And from the long list of measurement results, I run the maximum entropy algorithm to get the reconstructed density operator. So here, for that case, we measured 161 values of alpha. It was kind of 1 hour of measurement. We detected 7,000 atoms in 600 repetitions of the experiment for each value of alpha. So it gives you the time scale of the experiment and the kind of statistical you need to characterize the state. So here is the result of the density operator, represented as a matrix with the modulus square of the matrix elements. And if you switch this to the Wigner function representation, applying the mathematical formula I just gave, you get nearly the same as you expect from the theory. The noise is nearly not visible with this kind of statistics. So this is not an ideal state. It's really a reconstructed state. So you see that the state fidelity with respect to the amplitude we think we prepare in the cavity is 98%. So we have really a very good control over coherent field injected in the cavity by using a classical source. So let's go to more quantum states. And indeed, we prepare, now I will measure the function, the Wigner function for the number states prepared by the quantum non-demolition measurement process I described yesterday. So I prepare a current field. I send a collection of 100 atoms which project the field on a given photon number. I post-select all the experiments when I get 5 photons, and then I reconstruct the Wigner function of the 5 photon state. So we do this not only for, okay, unfortunately it was not done for 5, but it was done for photon number from 0 to 4. And you get for the vacuum a Wigner function which is a Gaussian centered over the origin. In this experiment, the statistics was not as good as the one when we characterized the current field, but it's still what we get. So it was this. And then for the 1 photon state, so you recognize the negative peak at the origin, the ring with some noise. So this gives you an idea of the noise in that measurement. Then for 2 photons, 3 photons, and you see every time you add 1 photon in the cavity, the Wigner function have 1 more ring. And so the peak at center, which is initially negative, becomes positive, but still you have some negativities in the first ring, which is blue here. And then for 3 photons, again, at the origin, the Wigner function is negative, and for 4, it becomes positive, but you have also blue ring who appears. So that's the measurement of photon number states, a Wigner function up to n equal 4, which is not so easily performed in any other system in optics. You can see Wigner function of the 1 photon state, eventually a superposition of 0 and 1 state, which looks like a squeeze state, it's not so easy to isolate a 4-photon state with optical photons. So now let's switch to the cat state. Instead of projecting the field of the photon number, instead of sending a collection of 100 atoms, I send only one atom measuring the parity of the field, detect this atom, this project the field of the cat state, as I described at the beginning of the lecture. And so we prepare this kind of entangled state as the result of interaction, which is projected either in that state or this state, depending whether the atom is detected in E or G after the second pi/2 pairs. And this is done by setting the phase shift per photon for pi, so that after interaction, we expect two fields with opposite phases. And indeed, an interesting property of this cat state is that there are well-defined parity. So there are two ways to look at this. When I measure the parity operator, the results have a given parity. If what I measure is a parity, I project on the parity state. So I expect that these two states have a well-defined parity, and the parity is even or odd. Indeed, you can also show it directly by expanding this alpha over the number states, and you will see that with a pi phase shift per photon, there is a destructive quantum interference for all odd quantum number states here, and you have an even cat state, whereas the quantum interference due to the minus sign here is destructive for even number states here, and you have an odd cat state. So we can prepare two kind of cat, and so depending on the measurement result of the first atom detection, we'll put the cat state either in the first or the second category, and then we use this state prepared by post-selection in order to perform a Wigner function reconstruction. And so that is the Wigner function reconstructed, I think in the case of the even cat state, in a situation where we injected in a cavity a small coherent field. And indeed, when we perform the reconstruction, we put in the system no a priori knowledge, except that the fact that the size of the Rydberg space cannot go to infinity, because we would need infinite number of measurement. So here we truncated for the reconstruction the Rydberg space to 9 photons, and we get this Wigner function reconstruction that I can comment by identifying two important features of that state. Here, you have two red spots corresponding to these peaks, which are reminiscent of the Gaussian Wigner function you expect for a coherent field with either a phase plus or a phase minus. And indeed, that's the classical part. And then the size of the Schrödinger cat, the relevant parameter to represent the size of the Schrödinger cat is the distance, which is homogeneous to a field amplitude between the two Gaussian or nearly Gaussian spots of this Wigner function. Indeed, if you analyze the state, you find that the distance square corresponds to a cat containing 7.5 photons. And you can see that the distance between the two spots is much larger than the size of each spot, which is more or less 1 unit as compared to 7. So it's already a superposition of two states which are large enough to be classically distinguishable. Then the other feature is the feature with negativities between the two components, the two classical components of the cat, which are the signature of the preparation of a coherent superposition. And that's what you expect from the Wigner function of an ideal cat state. So then we perform that reconstruction for the even cat, for the odd cat, and you have both reconstructions there. You can also reconstruct the Wigner function of the average state of the cavity field if you don't look at the measurement result of the parity. So it will just be the average between these two, which means that you still, when you average these two, have a good information about the classical component. The Gaussian two spots are still very visible, but as the phase of the interference is just opposite for the two cases, in between the fringes disappear. And the residual color here you have gives you an idea of the noise, residual noise of the measurement as compared to the signal. So signal to noise clearly demonstrate coherences here, which are not anymore visible here. So you can analyze this state in terms of fidelity with respect to the ideal cat. If the experiment was ideal, you find a fidelity of 0.7, which is not so bad for such a Schrödinger cat state, knowing that during the measurement, the cat already starts to experience some decoherence. So measurement is not instantaneous to reconstruct the Wigner function, and this explains this limited fidelity. So then, let's go to the next part. We have prepared the cat. How does it evolve? And how does it goes across the border between the quantum and the classical world? Well, the formalism to describe that is well known, and that's the interest of preparing a cat with a cavity QED technique, because we have a kind of very clean environment which can be described very precisely by this master equation. So you know that for long enough time, you expect exponential decay of the energy stored in the cavity, and you can model this energy decay by using some model where you couple the single mode of the cavity with the continuous mode of the outside world with some linear coupling between these. And when you run this model with coupled harmonic oscillator, you trace over the environment mode, and you get this equation evolution, this master equation for the field density operator with some Hamiltonian term, which just represents the free evolution of the field. Yeah, this term is proportional to the Hamiltonian. And then the term responsible of decay, which simply expresses as a function of A and A dagger operator. And then the physical result of this equation is that you expect decoherence, you expect vanishing of the interference term in the Wigner function between the two coherent spots on a time scale, which is the cavity damping, energy damping time divided by the photon number n. So that's an important result that you can have in mind. And now I will try to establish it, not solving this equation. It can be solved analytically, but with more handy argument. So how does it work, this decoherence? So, well, I will go one step back from the master equation, back to the model of a single mode coupled to a continuum of modes, which you can imagine the mode of the free field if you imagine that this environment has a size which goes to infinity. And then the decay of the coherent field can be described as a kind of Hamiltonian evolution. When you start with some, let's say for a coherent field, not a cat state, you start with a coherent field with a given amplitude alpha at time 0. You couple it with a vacuum of the environment. So I suppose environment at 0 temperature. We could adapt the argument with non-zero temperature. And how does it work? Well, when you have linear coupling between operators, you can solve the equation of evolution, and the result is that you have a state which remains coherent, but with a reduced amplitude, alpha of t experience exponential decay, which is related to the expected exponential decay of energy of the cavity field. And indeed, some beta coherent fields, small coherent fields, are growing in the environment modes. So environments, even if I write beta, it's not a single mode model, it's many modes, but each of the modes have a small field component beta. But defining a kind of a global mode for this, it's equivalent to a global small coherent field beta showing up in the environment. And you see that during evolution, there is no entanglement showing up. And indeed, if you look at the master equation of this spatial dissipation, the coherent field is the only one which does not get entangled with the environment during decay. So that can be considered the definition of the classical, quasi-classical states of the field. And it is a very important property which makes them so special. And indeed, that's why they are so classical. That they are robust, the coherent state character. There are pure states which remain pure and in the same family when they decay. And there is a kind of robustness of the classical information encoded in this state if you consider that this information is encoded in a classical amplitude. The classical amplitude decays smoothly without becoming entangled with anything. So that will be what, if I anticipate a little bit on the future, that will be the property which defines the preferred basis of a measurement apparatus. It is related to this robustness with respect to entanglement. So let us apply the same argument to a superposition state, a CAD state prepared in a cavity, a field with two phase components. So quantum mechanics is linear. So if I have a linear superposition of these two fields, alpha plus and alpha minus, each one will radiate in the environment a small coherent field beta plus and beta minus with the same phase of the original field. And so you see growing up in the environment two states which are making growing up a kind of kitten in the environment when the CAD state, the superposition of alpha and minus alpha, is decaying in the cavity. And then, indeed, you build some entanglement where you have a leak of information from the current field stored in the cavity into the environment. So you can say that the field in the cavity broadcasts information about its phase in the environment during decay. And then you see that if you trace over the environment state, you find that after some time, the coherent superposition here is dead as soon as the two states which are growing up in the environment become orthogonal to each other. There is no way. Once, in principle, there is enough information here, and enough information means that beta equals 1, more or less, the same amplitude as vacuum fluctuation. As soon as beta is large enough so that by looking at this, you know whether the phase is that or that, a complementarity argument tells you that the quantum superposition of two states here is dead, and you cannot describe this state anymore as a CAD state because of this leak of information. So you can finish the argument completely mathematically to get the precise value of the decoherence time. So here the argument is you calculate the scalar product between beta and beta minus to calculate the decoherence time. And then you get the amplitude of beta of t by energy conservation argument. So you know this decay is exponential. This gives you the expression of beta. You inject there, and you get a coherence time, which is of the order of the cavity damping time divided by n with a correcting factor related to the angle there. But I don't want to go into the mathematical details. So the point is that there is a quantum property of the CAD, the coherence of the superposition, which decays much faster as compared to the energy. And that's this separation of time scale, which is larger and larger where the system becomes bigger and bigger, so it becomes more classical. That is explaining what we call decoherence, that the fact that some observables are robust, some properties of the state are stored in the cavity for a long time, whereas some others are lost very fast by broadcasting to the environment. So here is just for the sake of completeness, the exact expression of decoherence time with the phase shift alpha. So now we observe this by repeating the full characterization of the state by its Wigner function at different delay between preparation and detection. So we prepare the state at a given time, we wait for some time, and then reconstruct the Wigner function. And here you will see the movie of the evolution of the Wigner function as a function of time, demonstrating the decoherence at work on the CAD states that we prepared here, with here two red spots reminiscent of the two classical amplitudes of the field involved in the CAD state, and the interference in between. So let's start the movie. It's not starts like this, but maybe like that. does not want to start. Okay. So when my connector, okay. So you see time is running, and as a function of time, more or less nothing or nearly nothing happened to the current spot, whereas the quantum interference in between, which were clearly visible initially, becomes just hidden in the noise. So I play the movie again so that you can see the beginning. So you have very clear coherences here, which disappear much faster as compared to the time scale. These two spots need to decay and to collapse to the origin after several cavity damping time. And so you see here with your haze, really the quantum properties of a field, which makes the field a good meter of the atomic state in the experiment, which means that the physics of dissipation, which tells you what is measured by the interaction with the cavity field. And what is measured is an atomic observable related to what is robust in the matter. And what is robust is the amplitude of current state and not the fringes, which are the signature of the cat state. And so here you have really a way to characterize in which basis your matter becomes classical. It's related not to the evolution of the atom, but to the coupling of the matter to its environment. And here we have the advantage to have a very clean environment that we can describe completely. So here are for a snapshot of this. From the density operator, we can reconstruct the amplitude of the interference term. We can plot it as a function of time. We can compare it with the theory, which is the line here. And we fit the decoherence time here, which is the black line. We find a decoherence time of 17 milliseconds plus minus 3 milliseconds for a cavity whose damping time was 0.13 milliseconds. So there is nearly one order of magnitude between the energy damping time and the decoherence time of this cat state. Then the theory gives for this cat a decoherence time of the order of 2 cavity damping time divided by the distance square between the two classical components of the field. When we put the number, we find 22 milliseconds, which is close to the expected value, especially if you add to the model the contribution of black body radiation, which slightly reduces the decoherence time in the presence of black body photons. So here, the prediction is 19.5, and we find 17 plus minus 3. So we are confident of what we have measured in this experiment. So then I will conclude with a resume of general consideration. We can draw about quantum measurement from this experiment. I think, I hope I showed you that the physical origin of decoherence is leak of information. Quantum theory is a theory of information, and you can consider the object you manipulate in quantum theory as the amount of information you have about some system. And if you perform a measurement, at some point your system becomes open, some information is leaking in the environment, which makes the projection of the state for you. It's not an abrupt projection at the time you look at the system, but it's already done for all practical purposes as soon as you open the box for a macroscopic Schrödinger cat state. So the experimentalist does not kill the cat, of course, when it opens the box. So you are safe. You are not guilty when you open the box. The job is already done, unfortunately. And indeed, nature or the environment already knows whether the cat is dead or alive well before opening the box. It means that the environment, we are not always aware of that, but always perform continuously unread measurement on the quantum objects we are considering, which makes them classical and which makes the world here, the table here, or all the objects here look classical. And then the collapse of the quantum states, which is introduced in the first lecture of quantum theory, can be considered as a kind of shortcut that you can absorb and apply very efficiently without understanding all the details about quantum measurement. But I think that the kind of argument here gives you physical insight of what is behind this collapse postulate. So then I can finish maybe with a more philosophical question, but I will not give any philosophical answer. The question is, does this solve the measurement problem? I think that all depends about what you consider as a measurement problem. You can consider that there is no measurement problem because the theory is consistent and in agreement with all measurements. So that is kind of my point of view of experimentalist. I have experiments which properly correspond to what I expect, so I have no measurement problem. Then you can think about, okay, but what is the reality of the system independently of what you measure? And from this point of view, I think if you want to have an explanation why quantum theory makes projection and in the end the system is not evolving in a huge superposition states that you can interpret with many word interpretations, but rather chooses one solution, I would say it's like this. I have not explained any mechanism producing this transition. So that's my point of view. And indeed, more pragmatically, I think a take-home message instead of philosophical consideration is the objective part of what we demonstrated, is that for meta, indeed, you have what is introduced by Zuret as a pointer basis or a preferred basis of the system. And this preferred basis, which is the classical state of the meta, is not defined by what I think and by my intuition, even if it corresponds, which is normal. But indeed, the decoherence approach introduces an objective way for defining the preferred basis. It is the basis of states which are more robust to entanglement with the environment. And in this basis, there is a general property of the density operator after decoherence, is that the diagonal matrix elements are still there, whereas off-diagonal matrix elements in the preferred basis are erased. And the existence of two time scale between damping of off-diagonal element and damping of the information, which will be damped if I wait too long, then is the physical argument which objectively defines what is a preferred basis. So when I say that, I am happy because I have a system where there is a completely unambiguous definition of the preferred basis. Of course, in most of the system is not so simple. And if I just reverse back the role of the atom and the cavity in my setup and want to look at decoherence from the point of view of what happens to the atom when it gets ionized, it's clear that the charge emitted by the atom and amplified interact with a lot of things, but I have no simple matter equation to write this and to say in the end that the preferred basis for this atom is either a click in channel E or a click in channel G. But in the end, if I try to model that with approximation, I can also get that. So that's the end. And so today we have considered generation of CAD states in the cavity, observe their decoherence. I would like to finish not about what we did, because I was very focused in all my talk, of course, on the experiment we perform, and I could not cover all the field of cavity QED, but I cannot not mention another very important field of cavity QED where everything I told you can be demonstrated in a very similar way because the system is very similar. It's the field of superconducting qubits, which was initiated by an experiment by John Clark, Michel Brune, and John Martinez, who got the Nobel Prize this year, and which, in this system, an important step was the introduction of a transmon qubit, with really very good artificial atoms, which behave very much with performance comparable to the circular Rydberg atoms. And I would like to acknowledge that, of course, everything I said there was also done with this system. And indeed, there was a fertilization from what we did to what they do. And I should say that now they reach a level of complexity by the possibility of integrating many qubits on a chip with many cavities that we cannot reach with our atomic system. And so it means that we now switch off the cavity QED activity And we are switching on another activity related to quantum simulation with a circular Rydberg atom that I will present in the two next lecture I will present at that school. So let me also acknowledge the collaboration, of course, with Serge Haroche and Jean-Michel Raymond, without which I think this work could not have been possible. I think this work is a perfect illustration of work which can be done on long time scale by having a long collaboration between people with different skills. And I think that, unfortunately, presently, in a world where you should have one project and one PI per project, it's not so easy to have this kind of experiments running. And I hope that there will be still some room for such kind of long-term experiment. And of course, this work was not the work of only the three guys, but here is the list of the people which were more or less involved in the evolution of all these cavity QED experiments from the beginning of the team of Serge Haroche. So the list started before I arrived there. And then all PhD students, postdoc, internship students which were there. And I would like to thank them before concluding this lecture. Thank you for attention. So I'm sorry I was a little bit longer than expected, but maybe we can take a few minutes for a few questions. I ask for the authorization by organizers. Okay. Mm-hmm.
Yes. Can you go back a few slides in the plot of the coherence? One more.
Yeah.
One more. Oh, after. in the plot of.
The graph, you mean? Yeah.
You said that the coherence makes that the probabilities are classical, but in this plot I see that you have coherence also in the steady state.
You mean we have we have? Sorry.
You said that in the steady state, your probability density matrix is diagonal, but in this plot...
Okay, so in this plot there is offset, you mean, this dotted line. So this is related to some imperfection and to the way we reconstruct the interference term. And indeed, the quantum superposition have some distortion, some noise, and we did not average this noise on the final state which defined the dotted line. So basically, when we fit a sine function on this to get a measurement of decoherence, there is an offset in the end. But it's just a technical limitation of the experiment. You should not trust this offset as a coherence.
Oh, okay.
We should have repeated the experiment more and more time to average it.
Okay, thanks.
Thank you for a lecture, Professor. I have like 2 questions, if it's not too much. The first one is concerning the preparation of cat states. So in the process, you mentioned that we must select a number state in the cavity by a QED measurement.
Yes, so for the reconstruction of the number state, I would say.
Yes, so does that mean we are producing a number state inside the cavity, or is the only part of the process of producing the
yes, indeed, depending on the state we want to measure, we did different experiments. So for preparing number states, we have not a source with just injecting number state in the cavity, because this is difficult. So what we do is inject the current state and measure its photon number. And by projection, you can post-select the measurement result where you get 0, 1, 2, or 4 photons. And then for each of these that you select by post-selection, you say, okay, that is my prepared state, and then you perform the sequence for measuring the Wigner function. Okay?
Okay. Thank you. So as for the second question, is concerning what you mentioned at the end on your conclusions for the origin of the coherence. So when you say that the environment is actually continuously measuring our system, how can I say it? Does the mere fact that the environment is interacting with our system already constitute a measurement, or is like a measurement is some kind of special
you can,
interaction?
In view that what does the measurement, the environment is interactions that you can call a measurement, and then it's unread measurement, because you never look into the detail of the measurement. So this measurement, when you don't read them, you trace over it, and you get the master equation for the density, the reduced density operator of the field. But that's unread measurements. You can consider that the environment performs unread measurements, and continuously, because you cannot switch off this interaction with the measurement. Here, the trick is that the time scale of dissipation of this unread measurement by the environment is so long, because it's related to the cavity damping time, that in the time needed to prepare the CAD state, this does not occur yet.
Thank you.
And then you have to wait so that it operates.
Yeah. Thank you.
Any other questions? No. Okay, so thank you, Michel.
Thank you.